All right, so welcome back to my YouTube channel. So in this video, I want to cover up transformer encoder. In the last videos, we have covered transformer encoder, but I'm not satisfied with the explanation that I've delivered. And I think there is more to it. There are some misconceptions also. When I was studying transformer, way back then, even I when I was studying, even I was not that good. It did took a lot of time for me to learn, but there are some doubts that I had when I'm implementing it, mainly when I'm implementing it. And I'm going to clear them all. Some there are some doubts, of course, so I'm going to clear them all. So first, let's go to the implementation that we have done in the last video. In the last video, we have developed transfer encoder, right? We have coded the scale dot product attention and multi-head attention and so on. And I think all of the misconceptions come from this scale dot product attention. So in the last video, I forgot to tell. I'm sorry, I have made a mistake here. I actually have to add a transpose function. I would transpose the last two. I would actually change the last two dimensions. So sorry for that. So sorry, -1, -2. I'm going to tell why this is required. It's actually one of the biggest doubts you will have when you are implementing transformer encoder. Like whenever yeah. So we are going to cover why do we have to transpose this k, and why also we have to divide this values by square root of dk. We are going to look at both of these things, why you have to do it, and also we'll be looking at, like, if you have learned about the transformer architecture and the scale dot product attention, you will know that we have to multiply the q, right? We have to multiply the q vector with all of these k values. So every key value we should be multiplied with this q vector, right? That is it. So for every word, so let's say the q vector for each word should multiply all the key vectors of all the words. But while implementation, we are not actually emphasizing it. So we are you might think that we have not done it. You might think that we are just multiplying the vectors, right? So that is actually multiplying the vectors. But this transposing is actually the reason why that operation takes place. The operation of the q value of the q vector of each word multiplying all the key values of all the other words. So that is actually, like, the process of, like, that process is actually carried out by this transpose function. That process is made true by this transpose function. So I forgot to put that. I'm very sorry for that. So first we'll learn why we did it, why we have transposed this vector. So to understand why we did it, yeah, I've already told you a reason why we did it. So the reason is, to actually enable that process. I'll actually come back to that in the last. But first, let's look at why we actually added the basic thing. It's actually pretty basic. So if you look at before that, we should first understand what matrix multiplication is. That is actually not very much complex. Matrix multiplication. So let's say you have some values here. Let's say you have two matrices, actually multiplying two matrices, right? So if you have matrices like this, so let's assume this, right? We have let's say these are q's. I'm not considering the dimensions here. Of course, the dimensions of q and k are I think 4-dimensional, right? So if you look at the implementation, the q and k are of 4-dimensional. If you think about it, sequence length 3-dimensional, sequence is length by number of heads by head dimension. That is q, right? So that is going to be qk. K is not k is going to be reverse because we have changed the dimension, right? So we are going to have, let's say this is q and this is k. Don't consider dimensions here. I'm just drawing this for examples, or I'm going to draw a different vector. Sorry, if I'm just going to delete it just so you can understand, right? So let's say you have, sorry. So let's say you have this 3 by 2 matrix, 3 by 2 matrix, right? So both are 3 by 2 matrix, right? So let's say each is word, and each word has, let's say, or like, yeah, like each word, each row is a word, and each word has like two keys. So anything, I don't care about the dimensions. So what we are going to do is matrix multiplication. In matrix multiplication, right? Matrix multiplication is all about multiplying these values by these values. So what we are going to do is we are going to multiply this value by this value, this value by this value, and this value by this value. But as we don't have like the number of rows is not equal to the number of columns, or number of, yeah, the number of columns is not equal to the number of rows, we cannot calculate the operation, right? So if you can think about it, before we are transposing k, q and k are of same dimension. So therefore, as the row of k does not match the column of q, we will not be able to perform the matrix multiplication. That is the reason why we actually twist, like we turn up the last dimension. So what we'll do is we'll just get this value. So we are just going to rotate this vector. If you think about rotating this matrix 90 degrees, even visually, you will get this value. So that is why we are going to flip this vector around. So that is the basic idea. And after that, you can just so as you flipped it, we can actually multiply this and this. So this value is multiply this value. So that is actually the matrix multiplication. So for that, we are going to flip the last dimension, right? So we are going to do that. For that, let's consider an example, right? So we have actually have had this notebook. I think a very old notebook, right? I have actually experimented like this, right? You can also do, like whenever you are learning machine learning, the shapes are very important. Like architecture is, I mean, architecture is the most important thing, all the process and all that. But after learning an architecture and when you are actually implementing, make sure to actually experiment, create as many Google Colab notebooks as you want, and just try to experiment, especially with shapes. So I have actually created this notebook very long ago. So not very long ago, but recently. So what I have done is I'm just going to, yeah, so I have just created a vector of k, right, of this dimension, 30 by 8 by 200 by 64. So both, what is 30? I'm just going to say 30 is nothing but the batch size, right? 8 is number of heads, 200 is max sequence length, which is nothing but the number of words in a sentence. And then we're going to have 64 dimensional k. So each q or each k is going to be a vector. So we are going to have k vector and we are going to have query and key value vector. So in this case, it is going to be a key value vector because I'm just representing it as k. So I'm just going to create a bunch of ones, right, just for our understanding of shapes. So we're going to have 64 dimensional vector of key. So the key vector is going to be of 64 dimensions. So we are going to have 64 numbers, and these numbers are going to be optimized in the gradient descent, of course. So if you look at the shape, we're going to have 30 by 8 by 200 by 64. Right, so we're going to have these. The shape is going to be this. So I'm just going to run it. Let's just print k, just for understanding. Let's just print k. How does it looks like? Right, so we are going to get a bunch of these values, right? So we're going to have a bunch of these values. Let's print the first value. Let's do this. Let's print the actual vector. How does that look like? Yeah, so we're going to have a bunch of ones, 64 ones, because we are going to have 64 values. And then we are going to have, yeah, so we're going to have 64 values and 200 sets. So for each word, we are going to have 64 values. And then after we have each word, so after we have completed for all words, it's for each word, we are going to have 64 values. And then after that, we are going to have 8 more sets like this because we are performing attention parallelly. So we are going to have 8 more query vectors, 8 more key values, and 8 more value vectors. So we're going to perform, as we are going to perform attention 8 times, we're going to have 8 more query key value pairs or query key value vectors. So we are going to have multiple understanding. So multiple attention vectors or attention, multiple attention. We carry out multiple attention. So we are going to have this value, and we are going to do the same for k. But we will ignore that. We'll do the same for q. We'll calculate the same dimension, and then right, if I do that, qk. So I'm just going to convert them into torch tensor, just so we can do the like just so we can multiply. I'm just going to create a new set code cell here. Sorry, I'm just going to create a new code cell. I'm going to say s is equals to torch dot matmul. I think it is I'm going to keep it here. So I think it is going to be nn dot. So I'm going to import torch dot functional as nn. I have taught about all of this in the last video. What is nn and all that. So I'm going to import torch dot nn dot functional. Let's go to the last part. Yeah, torch dot nn dot functional. Sorry, I'm going to import torch dot nn dot functional. So, sorry for that. Yeah, I'm going to delete this. Right, we're going to calculate this s. We are going to calculate s vector by torch dot matmul matrix multiplication between these gradient descent updated parameters. So a simple matrix multiplication between q and k. Right, so let's see if that works. Yes, it doesn't. Why it doesn't? Well, the dimensions doesn't match up, because as I've told you, told you the reason, the number of columns in the k vector should be equal to the number of rows in the q vector. So therefore we'll transpose it. So that is the reason. So if we transpose it, -1 from -2, if we transpose it, we're going to run it. It's going to work. Yeah, see, it works. So that is the thing. So if you look at this s dot shape, the shape of s, I'm going to look at the shape of s. Sorry for that. It is going to be 30 by 8 by 200 by 200 vector. So the shape, okay. So what we are going to do is, as I have told you, we are going to transpose the last dimension into the first, and the first dimension into the last dimension. So that is the idea here. So that is why we are doing this transpose function. That is why we are transposing the dimension. We are interchanging the last dimension such that the dimensions actually match up, right? And then so that is the reason why we use transpose, right? I think let's see if we have any more things in this notebook. Yeah. So if you look at now if you look at now after doing this, after let's just transpose it again. Let's say k equals k dot transpose -1, -2. Right. I'm going to transpose it again. And let's just look at the shape of k, just to understand the shape of k. What is going to be the shape? It is going to be so the last. So as you can see here, the shape of q is 30 by 8 by 200 by 64. So we are going to interchange this shape such that the matrix is actually inverted. So the last dimension is actually inverted, so that we can actually perform the process of matrix multiplication. So we are going to invert this 64 and 20, 200, just to make matrix multiplication possible. So that is the first misconception, and I hope I cleared that. The next thing is, why do we divide by dk? So I'm going to just give you a decent answer here. So if you look at if you think about it, let's say you have let's say your inputs and outputs are of huge amount of value. So let's say there will be a lot of difference between let's say the q and k. So let's say there are a lot of difference between this q and k vectors. So that thus uh, if there are values or numbers with higher difference, or the numbers are just higher, then you are going to have higher values. So let's say you have values such as 1,000 and values such as -100 or something. Then it computationally it is not going. The computer is not going to be very good. So like when you are doing machine learning, especially language modeling, you are thinking about lot of words, especially like if you think about ChatGPT, there are billion parameters. So there is going to be a lot of heads, lot of encoders, lot of decoders, lot of data. So therefore you want to decrease the computational cost as less as possible. And whenever there are huge differences between values and the values overburst, some values are given much, like some values of higher value than other values, we are going to destroy. We are not only going to have higher, like wasting higher computational power. We are not only going to waste higher computational power, but uh, we are also going to, like if you have lower values and values with lower variance, you I think you have heard about variance. I have already described it in the batch normalization video. So variance, if you have lower variance, then this training is going to be stable. So we do not give higher, like we are it the problem is called exploding gradients, when some gradients will be given higher importance than other gradients. That is called exploding gradients. Just to make sure this exploding gradients doesn't happen, just to make sure we don't give higher, very high importance to one value and lesser importance to other value, we'll divide by square root of dk. So dk is actually the dimension. So we're going to actually get the square root and divide by it. So the values are going to be much more smaller. So there will be no change to this, what they actually mean. So we are going to divide all of these values. So there will be no change to what they actually mean, what the computer grasp. But we are going to decrease the size. We are also going to stabilize the training, just like batch normalization. Normalization. So after you have performed this method, I highly recommend you experiment. Just take some two vectors qk, just assign them some random values between 0 and 1, and just try to calculate the mean and variance, right, before dividing by square root of dk. And after you do, if you actually calculate the, like the values and the mean and the variance, the mean is going to be very huge number, variance is also going to be very huge number. And after you divide by this math by square root of dk, the mean is actually going to be closer to 0. It'll come closer to 0. The variance will also come close to 1. So that is why it also acts as a batch normalization. So thus we also divide by square root of dk. So that is the reason why we use math dot square root dot dk. That is a second misconception which is also solved. And we are going to finally look at this thing, look at this other notebook. So how does transposing actually change the vector? So I have created q and k, again some random numbers. So not actually not random numbers, some ascending numbers, right? So we're going to have values from 0 to whatever this number is. This number is nothing but the product of all of these numbers. So what are we going to do is I have created um, a tensor called q. It is a matrix which has this shape: 30 by 8 by 200 by 64. Again, 30 is the batch size, 8 is the number of heads, 200 is the number of words, and 64 is actually the vector dimension of q for each word, right? If we look at the shape of q, this is the shape I've already told you. And then this is the q, this is actually q. If you actually look at q, nothing but 0, 1, 2, 3 values. So each vector is going to have 64 values from 0 if we count about it. And then we are going to have 200 vectors grouped together, right? And then other 200 vectors, and then finally 8 more different sets of this 200 vectors, which further consists of this 64 numbered vectors of query values. And if you have, and let's do the same for the k, but we'll just take this q and transpose it. So this is nothing but -2 -1 -1 -2. But as we are dealing with numpy, we are just going to do this 0 1 3 2. Let's going to shift the last two dimensions. So it should be 0 1 2 3. We're just going to shift into 0 1 3 2. So the dimensions are shift. Before, the dimensions are 38 264. Now the dimensions are 338, 64, 200. So we are going to shift. Now let's see how k is changed. Now let's see how k is changed. It's actually a very interesting observation when I have made it in the past. So what we are going to do is we are just going to, if you think about it, I'm going to print the first vector. I'm going to print the first vector. What is going to happen? Sorry, actually k, I think. Yeah. So we are going to have numbers. Yeah, we're going to have numbers from 0 to 1000, like what, 12,736, but with a gap of 64. So we're going to have 0 to 1000, 12,736 numbers, but with a gap of 64. And if we look at the second vector, it is going to start from 1 to 65. And if we look at the third vector, which is 2, we're going to have values from 2 to 1000. Now you do understand, right? So I'll just put the vector here, the k vector. So we are going to have this vector. I'm going to show the overall picture. So this is the overall vector. And if you look at it, observe closely, we are going to have these values aligned in this direction. So all of these values are aligned in this direction. So the first query vector is going to be aligned in this direction, so that we are going to have these values. We are going to reverse them and multiply them with the query vector. So that is how it works. So thank you for watching, and I'll just summarize this transformers encoder for you. There's actually a very good blog. I actually posted this link in the description. A very great guy, Mr. J. Alamar. I think he had contributed a lot. He also has his YouTube channel. I'll put the link of this document in the description, and also his YouTube channel. Make sure to check him out. So he actually explained it in a very decent manner. I definitely do recommend you check out this video, check out his blog. So this is it. This is a very useful diagram that you might have. You might just understand what is going on here. He's just explaining scaled dot product attention. So we are going to have right. So we will be just going to the bed. Yeah. So we are going to have input, let's say thinking machines. So these x1 and x2 are just embeddings that will be forming, and then we are going to multiply that by query vectors. So yeah, we are going to have multiply that by WQ vectors. We are going to have weight vectors, right? So that is why we are going to pass this into some neural networks and get these outputs, query key value vectors, some query key value vectors. We are going to obtain them, right? I'm just summarizing it just to make sure I understand. And then after we get these query key values vectors, so these are the query key value vectors. So we're going to have each key value vectors for each word, for each head. So we're going to have multiple process. I'm going to tell that in a bit earlier. So this is just single dot product attention. Let's scale dot product attention. So we're going to have one query, one key, one value set for each word, right? For each embedding. So we're going to multiply Q1 by K1. And then we are also going to multiply Q1 by K2. So this value, this is not just this value, right? So and then we are going to have get a value, and then we're going to divide by the square root of dk. Here the value is 8, right? And then we are going to do this apply softmax and multiply by v1, and then we'll sum it up. And this value and the obtained value of this softmax value, right? So this softmax value 0.88 and 0.212 specifies how much attention that word should give for that position. For now, in this case, the word thinking, we are dealing with the word thinking here. That is why we are multiplying with Q1. So as you might guess, the Q1 vector is this thinking word will give more importance to the word thinking rather than machines. So as you can already say by common sense, thinking will give more attention to the word thinking because they are more similar than machines. So we're going to even though it might seem pretty dumb, especially when you have a lot of words, it does make a difference. Maybe let's say robots, you have another word robots in the sentence, then you might think that you can you can pretty much say that this word thinking will give a lot of attention to this word robots, if there is a word called robots. And if we'll do the same for machines. So we are going to have calculate attention scores. So for each word, with each with other words in the question, in the input, we are going to calculate the attention, and then also for the all the other words. So that is the thing, and then we'll sum it up, right? So we'll have this z vector, right? And then we are going to, right, and then and after that we are going to have multiple attentions. So this is just one attention. We have calculated one z, which is nothing but the output of like one vector. So if you think about in neural networks, come back. If you think about in neural networks, you could have one neuron and one output. So this is the input and this is the output. What's happening? Sorry for that. So you could have one input and one output neural network. So input and output, you could have that, but you want more complexity, right? So why do we add more complexity? Or you might say, right? You can just say this, maybe like this. So you will add more complexity to this neural network, right? So I'm going to draw this. So you want to add more complexity. Why do you want to add more complexity? Well, because to find hard patterns, to actually make the model better, right? So if the to make the model understand better, to make the model find different patterns. So there are going to be a lot of patterns. So remember again to the back old days when I teach you when I teach you deep learning, or when you learn deep learning, like these weights are nothing but the features that are tracked in the input data. So or in the input data, if you think about CNNs and all that. So as if you have more complexity and more attention and more neural networks, or more layers in this context, we are going to have much more complex features and many features be tracked. So that is why we perform multi-head attention. Like deep learning has always been about building deeper models, building more sophisticated models. So therefore, we'll perform this multiple attention heads. Here say 8 attention heads. Why will we do it? Well, maybe different features are tracked, and maybe we make more accurate decisions. So that is why we perform it 8 times. So we are going to have eight attention values, 8 z values. I'm going to I just showed you how we can calculate z value. Make sure to check out this blog. It is very good. And then we'll sum it all up. We'll actually concatenate all of these values into ways and multiply that by W0. I actually showed you when we do that, right? So we have did this, and finally, after calculating scale product, we actually did this. We actually did an attention layer, right? We have did that. So and then so that's it. I think this is the encoder. This is positional encoding. I should also, I think, read that. I forgot about this. I should also probably read about that. The residual connections, layer adding a layer normalization and all that. Make sure to check this blog out. And thank you for watching. And in the next video, we'll do decoder from scratch, PyTorch, of course, Python. Then yeah, let's do this, and then yeah, see you in the next video.